This is Unit 5, Section 1. We're starting with geometric sequences and series. So first off, a sequence is any ordered list of numbers. So finite means that it ends, so there's a final term to it, whereas infinite means that it goes on forever. So the difference would be they either stop writing the numbers if it's finite, or they're going to put dot, dot, dot if it's infinite. We have what's called a rule. And a rule is generally written as an equation of some sort to describe how you get each term of the sequence. And the terms are based on position. So a sub 1 is the first term. A sub 2 is the second term, and so on. We use a sub n to denote any term in the sequence, no matter what the number n is. So if they're giving us the rule a sub n equals 2n plus 5, we're going to write the first 6 terms of the sequence, which means we're going to plug in the numbers 1 through 6 and see what we get out. So if I do 2 times 1 plus 5, I get 2 plus 5 is 7. If I do 2 times 2 plus 5, I get 4 plus 5 is 9. I get 2 times 3 plus 5, and so on. So 6 plus 5 is 11. 8 plus 5 is 13. You may already notice the pattern that's happening. 10 plus 5 is 15. And 12 plus 5 is 17. Notice we went up by 2 each time, and that was the number in front of the n. So the first 6 terms would be 7, 9, 11, 13, 15, 17. All right, let's do another one. This one's written a little differently. So this is negative 3 raised to the n minus 1 power. So for my first term, that would be negative 3 to the 1 minus 1, or negative 3 to the 0. And if you recall from Algebra 1, anything raised to the 0 power is really just 1. Then we would do negative 3 to the 2 minus 1, which is really negative 3 to the first power. And negative 3 not raised to anything really is just negative 3. I'm going to skip this part now. I'm just going to write negative 3 squared. So negative 3 times negative 3 is 9. Then we have negative 3 to the third power. So that's really 9 times negative 3 is negative 27. Negative 3 to the fourth power. So that would be negative 27 times negative 3, which is positive 81. And then the sixth term would be negative 3 to the fifth power. So 81 times negative 3 is negative 243. So the first 6 terms would be 1, negative 3, 9, negative 27, 81, and negative 243. All right, you go ahead and try these two, pause it, and you could check your answers. All right, so for the first one, I would have gotten 1, negative 2, 4, negative 8, 16, negative 32. And with the second one, I would have had 1/2, 2/3, 3/4, 4/5, 5/6, 6/7. All right, for these, we're going to describe the pattern that we see. We'll write the next term and then create our own rule. So generally speaking, what I would first look for is to see, are we adding the same thing or subtracting the same thing, or are we multiplying or dividing the same thing? If neither of those are true, then we're going to actually have to look at the numbers that appear and see if we can find a pattern within them. So if I look at my first one, I add 3, I add 5, I add 7. That doesn't work. Adding is not the same every time. Also, 3 times something gives me 8. It's not the same thing that I would multiply 8 by to get to 15. So it's not multiplication or division. It's not addition or subtraction. So I'm going to have to look at my numbers. Looking at these, they're all very close to perfect squares. I know 16 is a perfect square. I know 9 is a perfect square. I know 4 is a perfect square. I know 1 is a perfect square. So each of these numbers is actually one less than a perfect square. So if I say the perfect square is n squared, I'm really taking 1 away from that, right? 1 squared minus 1 is 0. 2 squared minus 1 is 3. 3 squared minus 1 is 8. So that means this would be our rule. And the next term, if I were to plug 5 in, 5 squared is 25, minus 1 is 24. That would be the next term. Looking at B, I could check the adding. Add 2, add 4, add 6. Well, that's not going to work. I could try multiplying. So 0 times anything is still going to give me 0. So I can't do multiplication on its own here. So really, 1 times 0 gives me 0, right? 1 times 0. And 2 can be written as 2 times 1. And looking at this, 6 can be written as 3 times 2. And 12 can be written as 4 times 3. So the term number I'm taking, right, term 1, term 2, term 3, term 4, each time I'm multiplying by one number less. So I'm taking whatever my term number is and multiplying by one less than that each time. So this would be my rule. That means my next term would be 5 times 1 less than 5 is 4, and I would get 20. So I know that these can be tricky because if you can't see the pattern, you're going to get stuck, and that's okay. But I want you to try the next two, pause it, and you can check your answer. All right, let's check these over, see if you got them. So the first one did in fact have adding between terms. So really we're looking at what did we have to start with. So if I added 2 from the previous one, I would have been starting with 1. So 2 times 1 plus 1, 2 times 2 plus 1, 2 times 3 plus 1. So 2n plus 1 would be my rule, and the next term would have been 2 times 5 plus 1, or 11. And in number 4, adding didn't work and multiplying didn't work. But again, these are numbers really close to perfect squares, right? 1, 4, 9, 16. So all of the numbers in my pattern here are 1 more than a perfect square. So this one would have been n squared plus 1. So if I did 5 squared plus 1, I would have gotten 26. So something we're not going to talk a lot about, but it exists, is something called a series. And a series can also be finite, meaning it ends, or infinite. And we can use summation notation to write a series. So really, a series is about the sum. So for a finite series, if I started at 2 to 4 to 6 to 8, and I know each of these, the rule was really 2 times the term number. So I could have written it as 2n, or in this case, I'm writing it as 2I. That means I'm starting with an n value, or a term value of 1, and I go all the way up to 2 times 4, so n, or I, was 4. So in the summation notation, we write what we started with and how many terms there were, and then the rule. Right? This is called sigma. Right? It's a Greek letter, sigma notation. For an infinite series, same problem here, right? Same numbers. So I know I was starting at I is 1 or n is 1, and I knew my rule was 2i or 2n. But since it didn't end, I wouldn't put a number on top. I would put infinity. All right? So let's just try to write each of these in summation notation. I know my first term, right? I is 1. And if I were to look at each of these, this is 25 times 1. This is 25 times 2. This is 25 times 3. And if I went all the way to the end, this would be 25 times 10. So I started at 1 and went up to 10. And my rule was 25 times the I. So for summation notation, I'm starting at I is 1, and I go all the way up to 10. And my rule was 25I. And that's all I have to do for this right now. For part B, it looks like I have 1 over 1 more than that, 2 over 1 more than that, 3 over 1 more than that, 4 over 1 more than that. So each time I have I over 1 more than I. So that would be my rule. I'm starting with I is 1, but that dot 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 means I go over to infinity. So to write this, starting I is 1 but going all the way up to infinity, we have I over I plus 1. All right, you try the next two, pause it, and then you could check your answers. All right, so here would be our answers. For number 5, we had 5 times I, right? 5 times 1, 5 times 2, 5 times 3, all the way up to 5 times 20. So it goes from 1 to 20, and the rule was 5I. For number 6, it was 6 to the first power, 6 squared, 6 to the third, 6 to the fourth. So my rule would be 6 to the I power, and it started at 1 and went all the way to infinity. Just something to note, you don't have to use the letter I. It could be anything. We could have kept it at N. It could be the letter K. It could be anything. And I does not have to start at 1 if we're doing a problem. But again, we're not going to worry much about series or summation, but I just wanted to show you what that meant. So there are 2 special types of sequences. Arithmetic is when you add or subtract the same amount to get from one term to the next, and geometric when you multiply or divide to get the same amount, multiply or divide by the same amount to get from one term to the next. So we're going to mostly be focusing on geometric, but to do that, we should really know how to tell the difference between the two. So we're going to determine whether each of these sequences is arithmetic, geometric, or neither. So generally, I'll check first for addition and subtraction because that's the easiest to see, and then I'll check for multiplication and division. For multiplication and division, I'll take the second term and divide it by the first. I'll take the third divided by the second. I'll take the fourth divided by the third, and that's how I'll check to see if it was multiplied by the same thing. So 23 to 15 was minus 8. 15 to 9 was minus 6. 9 to 5 was minus 4. We already know it's not arithmetic. It's not subtracting by the same amount. So if I tried to do 15 over 23, and let's say I did 3 over 5, or 5 over 9, none of these fractions are the same. So it was not arithmetic because we weren't adding or subtracting the same amount. It's not geometric because we're not multiplying or dividing by the same amount. So this one is actually neither. All right, looking at B, negative 9 to negative 2, we could add 7. Negative 2 to 5, we could add 7. 5 to 12, we could add 7. 12 to 19, we could add 7. So this one is arithmetic. Right? We added the same amount to get from one term to the next. In C, 2 to 6, we do plus 4. 6 to 18 plus 12. It's already not arithmetic. Let's check. 6 over 2 is 3. 18 over 6 is 3. 54 over 18 is 3. 162 over 54 is 3. So all of them reduce to 3, so that is in fact geometric. All right, so you're going to try the last set, pause it, and then you can check your answers. All right, so for 7, adding and subtracting didn't work, but if I divided 6 over negative 3, I got negative 2. Negative 12 over 6, I got negative 2. That was a geometric sequence. For number 8, if I tried adding, plus 4, then plus 5, then plus 6, so that's not arithmetic. If I tried dividing, 5 over 1 is 5, 10 over 5 is 2. Didn't divide either, so that was neither. And then number 9, I subtracted 3 each time, making it arithmetic. All right, and that is day 1 of chapter 8.